everyone. We are Julia, Alec, Marco, Julia, and Petrana. And we will present our project called Dark Patterns, How to Create Addictive Technologies. I would like to start my presentation by explaining what the partial shadow reinforcement is. So a partial shadow of reinforcement is a rule stating which instance of behavior, if any, will be reinforced. There are four types of partial shadow of reinforcement. Fixed ratio. Reinforcement occurs after fixed number of responses. Fixed interval. An exact amount of time passes between each reinforcement. Variable ratio. Reinforcement occurs after varying number of responses. And variable interval, the different amount of time passes between each reinforcement. The main goal of our project was to find out which type of partial shadow of reinforcement is the most addictive. In order to check, we conducted an experiment with the participants of Summer School of Science. The main task of participants was to press a button for which they were rewarded with M&Ms. We posted the following research question. Which partial shadow of reinforcement is the most addictive and creates the highest number of clicks? While our hypothesis was that variable ratio is the most addictive one and creates the highest number of clicks. Our experiment lasted 4 days. We divided people into 2 groups, each of 8 people. We tested variable ratio and fixed ratio on one group, and variable interval and fixed interval on the second group. Before starting the experiment, we gave our subjects the instructions about the course of the experiment. Participants were rewarded by pressing the button, but the frequency was different because different partial shadow of reinforcement were tested. After the experiment ended, the questionnaire about the course of the experiment was handed over to subjects.
Okay, after the experiment, we have gathered the data we needed. So we began by analyzing our data. We have begun by analyzing our data from which we have gathered through the experiment. Firstly, as you can see, our data is uneven. There is a lot of outliers. So So we wanted to analyze our data, but because we had such a limited number of subjects and so many outliers, we couldn't rely on regular methods of data analysis. So we turned our way for the paired t-test. In order to perform paired t-test, we had to do the log function of our data, and after that we could see that we had made our data normally distributed, so we could calculate the t-value, and after we calculate the t-value, we could calculate the p-value. Now p-value is just will show us the likelihood of our experiment is a result of a pure chance, or is a result of or it has some sort of correlation. But as you can see, our results are not that promising, since our percent that it happened by chance is 97%. But what we could calculate is the difference in the means of the fixed interval and a variable interval, which has the increase of 327%, which just shows how much variable rewards are more addictive than the fixed rewards. And as you know, all of you have fulfilled the questionnaire at the end of our experiment, and many of you had said that you were motivated to press the button again after you realized that you have been rewarded by pressing the button.
Our experiment had some limitations. Type of button changed, which resulted in different levels of attractiveness. Also, the sound of the button wasn't always indistinguishable from the other sounds, which could result in errors in the calculation of numbers of the clicks. We are only humans. Also, we tested small group of people, which resulted in high standard deviation. There are also people who don't like MMMs, which reduce their motivation. And what we could change? So we could build a program that counts the number of times the button was pushed. Then our data, our results will be more accurate, and we will avoid some errors. Also, the greater subject sample would help us to reduce the probability that our results are random. Not limit environmental distractions. We could eliminate the sounds and the voices of people who carried out the experiment, because sounds distracted some subjects. More consistency from the experiment, and arrangement of all elements should be constant for all the participants, and change the reward. As I said, not everyone likes MMMs. We could convert MMMs to money, for example.
Okay, so dark patterns, which is also the name of our project. So what are those? Dark patterns are mainly techniques used by companies to trick users into performing unintended and potentially harmful choices when using their products. Dark patterns and a few other things are several tools that companies can use to achieve their goal and make users do what benefits the company most. Those could be different tools or heuristics and dark patterns. So heuristics are shortcuts the brain takes when making decisions just to save energy. Okay, the result of our project is a little app we did in Figma, and the point of that app is a chatbot. If people want to talk to someone or are lonely and want someone to talk to, they can use this app. So this is the home screen, and there's a button here that is purple and asks you if you want to tell more about you. And then it asks you the name and pronouns, the age, and some interests, which are also totally applicable. And then you can continue through the onboarding process, and you will arrive at 3 choices. So you can select 3 people you want to talk to. You can select Mark, Amanda, or Alex. And here come the first tools into play that we use. So as you can see, the border around this is also purple, and that is not a random thing. That is because purple gets associated with the clicking of the buttons, since we make the other buttons purple, and also the placement is similar. Furthermore, we that is called priming, by the way, which is one of the tools I listed before. Furthermore, we also did some framing, because we placed this in the center, which makes it more likely to be clicked. And we also have 3 options, and want them to click the middle one, because people are most likely to press the middle or choose the middle of 3 options. Furthermore, there's also some fear of missing out, since these have way more options than the mark. And the length of the description also implies that it's better quality, as well as higher price also implies a better quality, or people assume it has a better quality, which are 2 heuristics. Okay, so we continue and we press on Amanda, and then you get presented with a little chat, and here you can see our pattern, which is bait and switch. It's a little one up there. And if you click on it, you get presented with a paywall, and it's actually not a feature you can use. You would actually have to pay for Alex. Okay, so here again, there's a lot of feature which implies this has a great quality, and you also have some fear of missing out because the voice calls with Alex could be very full, but you would have to pay for that. Then we focus on the main part of this, which is the chatting. And you might be thinking, how does our experiment play into this? And each message is like when you press the button. So it's a possible chance for a reward. And the reward could be interesting messages or special messages, like this one here. Want to know a little secret? So, with each message you receive, you have a possible chance of receiving such an award. And it is a variable ratio reward, which is based on the amount of messages you receive, and it is by chance. Furthermore, it is also purple around here, which again implies action, so you're more likely to stay in the app because you want to react to that and want to get rid of those purple borders around, just like Instagram stories that have the annoying thing on. So, that is our app, and we will continue with the presentation.
You didn't see that.
Okay, I would also like you to introduce to our team. So first you have me, the head of the imposter department. Then you have Julia, the head of the reward department. You have Alec, the head of Figma and other procedures. You have our project leader, Julia, the head of heuristics and statistics and hugs. And then you have the manifestation of sleep deprivation.
Okay, some more honorable mentions. We like to thank Leonardo, Eva, Ivana, and Chris for solving the statistical test mystery. We like to thank May for having the most M&Ms. She had 328 clicks, and for being the most curious subject. We also like to thank Bahar for eating all brown blue M&Ms and for breaking my program to check if we received an M&M. And we like to thank Borna because he wants to us. And most of all, we like to thank to everyone for being our lab rats and taking part in this experiment.
Twice.
Thank you. Any questions?
Okay, so can you give an example of partial scale differentiation by person?
Okay, so fixed ratio is, for example, I guess every fixed interval is getting a paycheck every month. Variable interval is checking an email. Fixed ratio is, for example, getting a free meal after 5 at 10. And
for example, social validations, which is when other people, it's, for example, on the app, it's the most popular choice down there. So it implies that other people use that or click on that choice the most, and that makes people think it is the best choice because other people do that. That would be social validation. Then there's also
Where are we? I think I accidentally switched screens, that's on me, sorry about that. There we go.
okay, there's also the ones I said, which is length implies strength. The more text you have, the more people think it is has higher quality. The same goes with price. There's also some we didn't use, which is, for example, made in Germany. You associate that with quality compared to like China. There's also loss aversion, which is not technically heuristic, but it is also it can also be used for your advantage when developing an app, which is, for example, when you lose $10, it feels very bad and like you lost $10. But if you win $10, you just win $10. So the losing of something has a greater effect on you than the winning of something. And scarcity, for example, when something or when you buy something online and it says special offer ends in 3 hours, you feel very pressured to make the choice to decide a product right now because you know it might not be available later. So those are a few examples of use cases. Yeah.
Did you test that people actually chose Amanda the most?
We didn't count it, but many people chose it.
I would be interested to hear the rest of these tools and dark patterns on the slide. If someone can go over, please. What framing of primary is
Maybe Marco can answer this question. Could you repeat that?
Can you please just go over real quick what these tools and dark patterns mean? This is
Sure. Some of the dark patterns, like pattern switch, are basically that icon you saw like a video call, and you click on it expecting to do a video call with the Amanda, but you get the paywall with Alex. So you have been baited into clicking the icon, and you expected something else, and then you didn't get it. So they present you with a solution to that problem. Like you can now pay us, and we will allow you to have a video call. So you're more likely to buy than that function which you would like to have. Maybe some tools. For example, framing. Framing is the most common one. You can most common method of getting you to do something. Basically, everything is framed on every website. For example, some things are hidden from you, like in small letters. Some things they want you to click are more like have something around them, like an icons. They are colored, and you're just more likely to press them. They are in the middle of the screen, for example, like we did with Amanda, and we want to increase the chance of you clicking the specific button. For example, accepting cookies on some websites or something like that. Anything else you're interested in?
I would be interested to hear all of them if you want to go over. If someone asks a question.
Angela had a question, so maybe you can ask them after the lecture. Okay.
What's your hypothesis from the beginning that this variable ratio is the most addictive?
Yes, well, exactly from the beginning we think that the variable ratio is the most addictive one. We looked at examples, we talked about situations that we experience in our lives, and we found that this one is the most addictive one.
They didn't know. They just assumed, as Julia just said.
But where did the assumption come from?
Well, that's what she was saying, from looking at life and looking at
Just
examples.
like, okay.
Can you go to the results slide?
Which one there were several?
The graphics ones.
Okay.
What do these columns represent? I didn't really catch what the three the columns are.
So basically, we had the raw data which we couldn't represent so we couldn't use this data to calculate it, to perform t-test, to get the t-value, because it is not normally distributed. So we took the log function of this data to get data we could normally distribute. So if you look at those box charts, you can see they are symmetrical. So that's the proof that they are normally distributed, and we can use this data to perform t-test. This column chart basically just represents this data. We didn't want to include another table in our slide, so we just put the column in. It basically just represents the log function of our data on the previous slide.
Okay, so do you think that like forming an addiction or like falling for these dark patterns has anything to do with someone's personality traits? Because you were talking a lot about how different people approach all of this differently. Some of them didn't even feel like pressing it or pressing it more than once and so on. Do you think there's any correlation between maybe someone's personality and falling for this, or do you think it's pretty universal?
Well, it depends surely a bit, but I think that people like corporations and people who do designing are just trying to frame their websites and try to bait you into doing things that you otherwise might not do. For example, if you are represented with the accept cookies when it pops up, and you just see the big red button, for example, or big blue button, and you press it, just accept cookies. You don't want to read through all this nonsense, basically. And you just want to get rid of it, and you see the thing, and it is pressed out, it comes to you, press it, because it will get rid of it. But, for example, some people do choose to go through all of it and reject cookies, for example. But most people actually do not care, and just the impulsive reaction, just get rid of it and press the button. There is most like attracted to them, for example.
Okay, maybe one short question.
Alex can answer.
Did you actually prove your hypothesis?
Well, it was the correct hypothesis, but the experiment didn't prove it since it,
Which one?
the one that was the scary number. So as you can see here, we have a 97% chance that the data was rendered by random like this. So we sadly didn't prove it, while the data was actually, or the number of clicks were actually the most with the variable ratio. It is not proven since there's no statistical significance to that. I hope that answers.
Just as a final comment, I would say, you performed t-test on actual data that is not normally distributed. And I think that, for example, this 300%, it's impossible to have such an increase due to a random chance for that much samples. So I would say that rather your statistical analysis is skewed than you not having proven your data, your hypothesis.
Yeah. But then after log transform, it is more or less correct.
Yeah, but I mean, can you do it to such a small sample of data?
No, like the sample size is the problem.
Yeah.
Yeah,
This,
you know.
this increase in percentage is actually the increase in the mean. It's not the increase created the mean number of clicks in both fixed interval and variable interval, and then we calculated what's the percentage increase from the fixed interval to the variable interval.
Yeah.
And that's that increase.
But I get that, but I just think that 300% doesn't happen in nature.
Yeah.
So in a way, it was proven, but it showed that summer school science is it has limitations to it.
Yeah.
Okay, we ran out of time. Can I ask you, what was Amanda's little secret? I guess you'll have to pay to find out. Oh.
I would like to give you the certificate and thank you for participating.
Yes, please.
Just put yours.
Can you come maybe here?
Yes. Here.
Go among your pictures.
Where?
In the middle.
Just show me your certificate.
What? But I'm way too tall.
You look like small.
This is not gonna work, I think.
Sorry, I just
Everybody smile. Say cheese. Cheese. Say dark patterns. Dark patterns. Very fun.
Chris, you're popcorning the
well,
next
I'm
one.
popcorning with someone.
But with everything, come on.
I popcorn Anton's tree.
So you get to decide. Do you want to tell your one?
It's on the table.
Perfect. Clickers on the table. Yes. People, have you heard? Play that one? You know where the picture is. I said it a million times, and you don't listen when you don't get it.
What? You don't get to click it.
Well, then listen. I said it 3 times. Perfect. Thank you. Marco, now you know where it is.
Okay, are you ready? Just a second. We can set up our timer too. Okay, yes, we're ready.
Ready?
Yes. Okay. Okay, so good evening, everyone. In the last few days, Bahar, Marco, Stian, and Anton and I have done a project to construct a particle detector from scratch.
You have the
Oh, sorry. So we constructed. This is the layout of our presentation. First, we'll introduce you to the topic and give you a brief history of the cloud chamber. Then we'll introduce you to the theory and how our experiment will actually work. Then we'll tell you about the analysis and how such images can be analyzed, and the conclusions and what we actually found. First, a brief history of a cloud chamber. Actually, it was first introduced in 1911 by Charles Wellston. It was actually his accident because Scottish physicists actually wanted to study cloud formation and optical phenomenon in moist air, but he soon realized that he had accidentally discovered a particle detector. Through the first half of the 20th century, simple devices like this were used to discover subatomic particles, which led soon to the discovery of the positron in 1932 and the discovery of a neutron in 1936 using an expansion chamber by Carl Anderson. He used an alcohol as a solution and applied a strong magnetic field to actually do his cloud chamber, for which he got a Nobel Prize, as well as Charles Winston did 10 years ago. To explain the actual working principle of our chamber, what we have inside, the only thing that is inside our chamber is actually the concentrated isopropanol or isopropyl alcohol. But the conditions are which makes it a cloud chamber.
So having it be a closed space and having a large temperature gradient from the top to the bottom of the chamber, we essentially get gas, which then drops because it's much heavier than air. So the concentrated isopropanol drops, but as it drops, it cools down quite fast. It cools down to a temperature where it's a gas, but it's not supposed to be a gas at that temperature, which then it became a supersaturated gas. In this form, the results is that the alcohol is in a gaseous state, but at the temperature where it normally can exist, which means that therefore it will easily condense into a liquid state if anything disturbs it. This means that if electrically charged particle passes through, which we can see, the supersaturated layer forms into drops, and ionized gas defines the trail of our particle. This is enough to start the condensation process, and this is the actual reason why we can see the path of which the particle has passed. Why? There are very large differences in trails according to what particles actually pass through our chamber. First, we'll start with electrons and positrons. Electrons and positrons leave quite thin, but also scattered patterns in our clown chamber. Because they have such little masses, they tend to scatter more than stationary particles. Hence, we don't get such clean lines that we can see with muons, for exactly. They form curvy lines because they have very low momentums. And compared to protons, for example, proton lines, they're much, much thinner. But when we look at alpha particles, which are the lightest, consistent of 2 protons and 2 neutrons, which is the least penetrating radiation, we get, and it has a charge of 2+, we get those massive short wire trays. They can be seen in pump chambers during the demonstration of the thorium decay chain following the ejection of our isotope. And what we can actually see is the shorter and the thickest trail we can get. Then we get muons, which are made showers of cosmic ray particles that come high in Earth's atmosphere and leave a very long trail. Compared to, for example, electrons, they're really straight because of their very high momentum of the particle. So in order to actually be able to explain the path of particles and to actually differentiate between positively and negatively charged particles, we need to apply a magnetic field across the cloud chamber. And if a magnetic field is applied across the cloud chamber, it positively and negatively charged particles go to different directions, and then we can differentiate if it's a positive or negatively charged particle. The magnetic force acts as a centripetal force, forming a spiral movement of the particle with a gyro radius shown here. So P being the momentum, Q being the charge, and B being the magnetic field. But knowing the mass, not knowing the mass, but estimating the perpendicular to the magnetic force velocity of the particle, we can conclude on the mass and on the charge of the particle, and actually conclude on the particle identity, which allows us to actually know what the particle passing through our chamber is. In order to be able to do this, we need to embed the chamber into a magnetic field. The easiest way to do this is by producing a Helmholtz configuration, which we've done and shown in the picture. This is the properties of our Helmholtz configuration, and actually in our setup for the parameters were as shown, and we managed to actually produce a magnetic field of 425 microteslas with the already existing background field of the Earth. This would allow us, if our experiment would have succeeded, to actually differentiate between negative particles and positive particles, and to actually determine which particle it would have been. Now that we explained the magnetic part of the experiment, we can move on to the kinematics or moving particles, which is basically based on the particles experience time and space differently than the observers at rest. What we can see here is that time and space behave differently when the particle's velocity approaches the speed of light. When particles are moving close to the speed of light, the Newtonian notion of relativity breaks down, which means that the coordinate transformations that we're used to cannot be applied for their motion anymore. There we base the Lorentz transformations derived from Einstein's postulates, and actually time dilation enables us to observe particles that otherwise would have decayed. So we can observe the prime system with the actual first system. The consequence of this is time dilation, which actually explains us how the faster we move in space, the slower we move in time. For example, it allows us to see muon when in reality their mean lifetime is only 10 to the minus 6 of a second.
So, cosmic rays, where do they come from? Where do they go? Cosmic rays is basically an umbrella term that encompasses all high energy particles that are created because of cosmic events such as quasars, supernovas, or basically just the nuclei of big galaxies. And this basically how these particles actually get this ludicrous amount of energy is by a phenomenon that's called the shock front acceleration, where basically you have this little particle between two shock waves of, let's say, a supernova. And it's like two tennis players playing with a tennis ball, but at a certain point, the other tennis player does not manage to hit the ball, and the ball goes off flying at some percentage of the speed of light. That's where the time dilation is actually shown, because the mean life of these particles is incredibly short, something like 10 to the negative 9 seconds. And basically, the faster we move through space, the slower we move through time, and we would have been able to actually see these particles if we managed to get the detector to actually work. There are two types of cosmic rays, but they're basically one of the same. There are primary and secondary. The primary are basically the ones that get ejected, and ones that get ejected are mostly protons and bigger nuclei. A small percentage of it are actually electrons and a bit of alpha particles. And the secondary cosmic rays are the ones that are created after the primary cosmic rays encounter another particle, and they smash into that other particle, which basically causes them to scatter into a lot of different particles that all have smaller energies. And those are the particles that we also wanted to measure, because our atmosphere is very good at doing this scattering. So first, we need to understand a few things about the standard model and a few things about the particles that I talked about. So the standard model is one of the most successful, if not the most successful physics model ever created. And basically it encompasses the electromagnetic force, the strong and weak nuclear forces. However, it doesn't encompass gravity, both because gravity's effect on particle interaction is negligible, and because it just doesn't fit within the standard model elementary particles. The standard model elementary particles divides particles into two categories: fermions and bosons. Fermions are the particles that construct matter itself. They're the most basic building blocks, and bosons are the force-carrying particles that allow the actual interaction to occur. The difference between these two are the so-called spins, which is an inherent thing that all elementary particles have, and basically that's the reason why they interact the way they interact. So you might have seen in the standard model, in the fermions category, we have quarks and leptons. Quarks are the ones that create hadrons, the larger particles such as protons or neutrons, and these quarks can also be rearranged in many different ways to create all sorts of other baryons that are also the constituents of matter, and they have a spin of 1/2, whereas things such as the bosons that carry the forces have either a spin of 1 or a spin of 0. Anyway, it has to be a round number. And these mesons, so mesons are particles that are created from quark anti-quark pairs, and they also act as force-carrying particles in many different parts of physics. For example, the plus pion is the main reason why the nuclear force works as it does, and it's the main reason why we just don't explode and we are kept together by the gluons that are at action and by the quantum mechanics that we've learned about during this project.
So yeah, I'll talk a bit about how we made our chamber, and it has actually quite a few parts to it, even though it's in theory just a box with data inside. The last one of our designs, we had quite a few of them, is the one shown in the picture, where we had a box with crushed up dry ice with a metal dish on top, where we placed an aquarium upside down on top of it, and taped it down to make sure that it was airtight, and then placed a hot water bath on the top. And we also made a magnetic field, which we did by winding some coils, a couple of them, and we mounted them into some styrofoam pieces. And for the actual keeping the chamber cool, we first attempted to use a mixture of normal ice and salt and alcohol, but we think it didn't get cold enough, so we had more hope when we got the dry ice. So here's a couple of the configurations we attempted. And if you, so the dark blue is the hot side, and the other color is the cold side. So first we attempted to have the cold side on top and the warm side on the bottom, which introduced convection in the system, which then would make it impossible to see any particles because the air inside it would be moving, where we require quite still air. We then moved on to having the ice on the cold side on the bottom and hot side on the top. First we attempted to have the alcohol on the bottom, but the problem there is it wouldn't vaporize, and then therefore the air wouldn't be super saturated as we needed to be. We attempted to have some, we used towels and sponges, tried some different to soak the alcohol in, and then let it evaporate out of them. So if you could go to the next slide.
Yes, and I will be telling you about the analysis. So if our experiment would have worked, we would have been doing something called the hot transfer, which is an algorithm for image recognition. And you can use it for linear, cylindrical, and other types of lines you have in the pictures you get. So we would have been using it for cosmic rays if our experiment would have worked. So the algorithm works like this. You get a picture, you find the edges, and then it detects the lines. So the math of this algorithm is really simple. Most of you already know NX plus B, but what the algorithm does is that it represents our data as points on the line, and we find the origin, and we find distance between the point, which is our data, and from the origin to the point, and then we try to represent it in the straight line. So if we were to have the task to find the blue line, and we have certain points, and we start from the first point and draw random lines in order to find the blue line, we'd see that if we do this and measure the distance from the origin to the lines we draw, we get the result 60, 60, 60 in all of them, which means that we have found our desired line. And this is how the algorithm works. So we put the code, we code this algorithm in Python, You can code this in other languages too, but we chose Python because it's simpler, and we used a library called PIL, Python Image Library. And we had to modify the code because of some complications. But we borrowed the code, the sample code for the algorithm. And in order to make sure that it actually works, we tried it with a simple picture of pentagon. And you can see that they have 5 points that are darker, and they are representing the 5 major points of the pentagon. So we made sure that the algorithm works. And then we tried it with a simple picture of cosmic ray of what we would have gotten from our experiment, and we get the black picture on the top right side, which showed us that we have to have white background and black lines instead. And when we modified the picture, we got the correct result with darker points. So in conclusion, we didn't manage to actually have a proper result, but we learned a lot about theory of particles, and we learned how cloud chambers works. We tried to construct one, but it didn't really go well. But we successfully modified the algorithm we found for Hop transform, and we learned more about it, and we learned that we should never give up.
And lastly, we'd just like to say that we really enjoyed trying to construct a cloud chamber. We would like to thank Anton for mentoring us along the way. And lastly, thank you for listening.
You spent 14 minutes just explaining the theory, and the rest, like maybe 7 minutes, on actually giving a talk on your experiment. So maybe for the future reference, it should be rather 5 minutes of introduction and rest what you actually done. Questions, 10 minutes.
If you were to do the cloud chamber again, like if you had 3 more days, what would you do different? What would you now try out? Do you have any ideas?
Maybe I can answer the question. There are several things that could have explained what we have done wrong in our chamber. The first thing is not actually achieving the problem, but the proper temperature gradient needed in order to produce the certain amount of vapor. The other thing is that we have conducted this experiment quite low below the ground in the atomic shelter, which quite blocks most of the actual paths that we have gotten. And in order to do this better, we would have isolated the system better, provided a better gradient of the temperature, and if this was possible, provided a dark room, but somewhere higher in the building.
Why did you use angle representation for, and not the, I mean, I have some assumptions, but it's not fully clear for me. So why did you transform your lines into the angle transformation instead of using the Cartesian coordinates, Cartesian being the standard?
You mean the first picture we had on?
You know how you express your line, mx plus c, as a combination of cosine and sine?
Yeah.
Why do you do that? Why is that representation better than the first one?
First of all, because the first one doesn't really measure the distance from the origin to the point. The first one isn't really measuring the distance from the origin to the line we draw, so we kind of had to use the second one. And the second one is like more of a convenient way of writing it, and like it's a standard way. We have seen it, but it also the main problem is mostly because of the distance for the origin, since the picture is connected to the next slide about PQ.
So
for this.
So and the other really important problem is that computers can't use that method to represent vertical lines. And that's a problem because we want to do that as well.
Okay, so it's related to, because the computer basically measures it the origin or the center. And you mentioned the vector, something vector.
No, if you would try to represent a particular line with that method, you would run into problems with infinite
With the
infinity.
code, because it will just go straight up, and the code doesn't really work.
Okay. So yeah, then that so then because you have angles here from like you limited to like angles from 0 to 360, I guess. So then basically the line just stops at some point.
You mean the line here, or?
Yes.
Yeah. Could you go back to the next? No. The lines doesn't really stop at some point. There are arbitrary lines you draw in order to find the right line. For instance, the blue one here is the right line because we have our points on the blue line. It could have been another line in some other shapes where you had your points, but it looks the same.
Yeah, thanks.
Can I ask would you have used the data you obtained from the particle detector if it were?
Yes.
Yeah. Could you go to the picture with the black thing we got? We would have done the same thing like this, but with the pictures we got from our chamber.
And also we could have done it by measuring from two sides. So we could have actually done it in 2 dimensions.
Yeah, we would have been more exact.
And also apply a magnetic field, which was also built. So the only missing thing was the particles.
Can you maybe explain on this slide what do these? So on the right you have something that the program made out of these pictures. What does it represent?
So these are the one before. It's the better picture.
Maybe Marco can answer.
Yeah. Oh, sorry.
So these are the parts that the program spits out.
Noise.
What do they represent?
It's the things that you see, the lines that aren't as dark. That's the noise from all of the surrounding color. And basically we have to have a really good background and a really good trail to not have this happen to us. Because you see there aren't really any like extremely dark lines, which means this picture didn't have really specific points, I guess.
Yeah.
I'm not the programmer, sorry.
It's pretty much the same. The dark places are where you are more likely to find a point. But the other places, because the code, it works like this going up, like imagine it's like a car that goes like this, try to find like a correct place. And where you find the actual point, it stops. And then it continues going on.
Okay.
Again.
Maybe.
Can I ask for clarification on, because you said you would have used this method, but what exactly does this show you about the particle? This Q, does it show you the path of the particle from which you can calculate its nature?
It would show us the path the particle took, and if we would have photographed it from 2 angles, we could have represented it in a 3D space and seen where it came from.
And also, like we already clarified, if we could have actually done the experiment with the magnetic field too, we could determine the radius of the sphere and then actually retroactively determine what the particle is that enters our chamber.
How much time do we have left right now?
3 minutes.
Any other questions?
Yes.
Here. I just have like a few simple ones. So in this chamber, because you have like hot water on one side and then dry ice on the other, do you have an idea? Did you measure the temperature gradient actually? So did you somewhat roughly knew what temperature you actually have at the bottom and the top? I mean, of course, it assumes to have the temperature of a dry house and like a bit less than 100 degrees, I guess. But did you actually kind of check, you know, how the temperature distribution was, or like how the temperature gradient was throughout the chamber?
No, we didn't exactly check it, but theoretically it could
somewhat linear, kind of from one to the other, or is it kind of like very cold?
Would assume so.
Hmm?
Would assume so.
Okay. Okay.
That could have been a good idea, maybe for the improvement. Okay, so first thing, you mentioned several times that you don't think, while speaking to me, not in the presentation, that you don't think that the atomic shelter has affected the particles, but only has slowed them down. So could someone explain why they haven't been absorbed, but why they have been slowed down by the atomic shelter?
I mean, they go at a fraction of the speed of light, which is of course the biggest velocity anything can have. And the fact that they have inherent mass means they interact with other like mass particles. So for example, we would have had, let's say, a positron or an electron, and that electron would have been emitted, I don't know, let's say 1,000 years ago, and it travels, and it has to travel through all of the atoms above the actual atomic shelter, and then when it finally hits our cloud chamber, the reason why we actually did it down there, we didn't actually think about the gradient that much. The reason was so that the velocity wasn't too high, so that our little chamber can actually capture the ellipse that was supposed to be formed by the homogeneous magnetic field. Because a straight line, we can always interpret the straight line. It could have been up there, but if we were to use the homogeneous field, this would have been a lot easier, because we would have had a kind of complete ellipse.
You mentioned something that time dilation is important because these particles sort of exist or are stable for a fraction of a second. Is it correct?
Yes.
So that if they get slowed down by the atomic shelter, doesn't that mean that they sort of decay before they reach the particle detector?
Yes, that's back to the thing that it's going incredibly fast, and even these 3 to 4 stories isn't much to go through when compared to the actual speed of light, and that's why it doesn't slow them down that much to the extent that we can't measure them, but it slows them enough just right for us to do the experiment, but we didn't manage to do the chamber, so yeah.
Just to put into reference, some of the cosmic rays that we actually could have measured actually penetrate the Earth as a planet. That's how fast and the magnitude of their speed of their trajectory is. So the thing that we have like 3 stories is not really significant to that extent that we don't have to.
Especially particles that don't have inherent mass, that are massless.
Which are the ones that we expect.